Solving x prime equals ax is slightly tricky. In this case, we have seen a procedure that gets the job done. In this video, we will apply this procedure to an explicit example. We have x prime equals ax, and here we have our matrix A. So, first we compute p lambda, we need the eigenvalues. So, add the minus lambdas, compute the determinant, so minus lambda times minus 2 minus lambda minus 1 times minus 2, so minus minus 2 plus 2, mind the signs, work out the brackets, and we get lambda squared plus 2 lambda plus 1. We have to set p lambda equal to 0, so we complete the square, we get lambda plus 1 squared plus 1 equals 0, or lambda plus 1 squared equals minus 1, so lambda plus 1 equals plus or minus I. And our first eigenvalue, we have lambda 1 equals minus 1 plus I. And as our second eigenvalue, the complex conjugate lambda 2 equals minus 1 minus I. Now we need only one eigenvector for our solution. Well, if you have found one, we also know the other because it's the complex conjugate of the first one. So then we are there anyway, but we need only the first one. Well, take one, let's take lambda 1 minus 1 plus I. We compute a minus lambda 1 times I, add zeros and do some row reduction. So here we go, here we have a minus lambda I, already added the zeros. Well, row reduction, even in a 2 by 2 case, in the complex case is slightly annoying. Let's multiply the first row by 1 plus I, because by doing so, we get rubbish on the first position, but a 1 plus I on the second one, which is the same as what is in the second row. So that's what you see happens here. We get a nice 1 plus I here, which will cancel with the minus 1 minus I. And the first component, 1 plus I times 1 minus I, becomes 2. We add this row over here once, and we get a row with zeros. Of course, we get that because we need a free variable. Otherwise, we would have gotten only the zero solution, and we wouldn't have found an eigenvector. So this is always a nice check. If you are looking for eigenvectors, if you do this row reduction, in the end somewhere a free variable should pop up. And since this is only a 2 by 2 case, it will pop up very fast. On to solving. We know C2 equals 3, and the first equation gives us 2c1 plus 1 plus I times c2 equals 0, or solving for c1, we get c1 equals minus 1 minus I over 2 times c2. Put it in a vector, so here we have our x, our solution vector. Then we can pick any c2 we like. In this case, I like to pick c2 equals 2 in order to get rid of the fraction. So here we have our eigenvector v1. So there we go. Up till now, just some linear algebra. Moving on to solving our differential equation. So what did we need? We need u of t equals v times e to the power lambda t. So there we go. And then we have to find its real and imaginary part. So first leave the v where it is. E to the power minus 1 plus I times t gives us e to the power minus t times e to the power it. And e to the power it equals cos t plus I sin t. And then one more step. So the first component is slightly messy. We get this e to the power minus t, of course, here. We get the minus cosine t, minus I sin t, minus I cosine t, and a plus sin t. That's the first component. And the second component is easy, of course. That's just 2 times cos t plus 2 times I times sin t. And then we pick real and imaginary parts. So the x1 of t, our first independent solution, is a real part of u. So for that we get minus cos t plus sin t times this e power as first component and 2 cos t as a second component. So there we have our first independent solution. And the second one is the imaginary part. So minus the sin t minus the cosine t, there they are. And a plus 2 sin t over here. That's the imaginary part of u, is our x2 of t and is our second independent solution. And our full solution is, of course, any linear combination of these two. So x of t equals c1 times x1 plus c2 times x2. So there we are.